verify Fibonacci formula. Two parts, and this part we only work on special cases. Next video we work on the general case. All right, so our goal, we want to verify this formula. All right, yeah, but we feel it is pretty hard, right? And when we start, we only work on the simplest a few cases. So that means when n equals 0, 1, 2. That's pretty simple, but in order to, challenge our skills, algebra skills, we also try n equals 3. Can we also verify n equals 3? It is pretty hard, but we will try it. Yeah. All right, so let's start the verification. Powerful tool. So why we start from these simplest cases? Very simple. Because later, when we apply mathematical induction, we need to verify the base cases first. A few base cases. Yeah. So that's the reason. Yeah. All right. 0, pretty easy. You plug into the formula 0. Yeah. So phi to the 0, that's 1. 1 minus 1, 0. So we get 0. Yeah. F1, this time a little more work. Yeah. But the second fraction a little more complicated because there is an irrational number at a denominator. But we know, so there is a commonly used technique. Yeah, we convert this fraction to another fraction, but the denominator is a rational number. Okay, so this step, we rationalize the denominator. All right, yeah. The way we do, yeah, I hope you know the scale, right? So we multiply this fraction by, yeah, so here, how to do that? We do it in this way. Yeah, you multiply root 5 minus 1, root 5 minus 1. Okay, yeah, multiply to this fraction because that's 1. That is 1, right? So multiply to that, our second fraction. Yeah. So after you do some simplification, you get that. All right. So with that, now, after simplification equals 1. So first, correct. Second, also correct. The third one, yeah, this time we just do a little more work. Yeah. But still, we can handle, right? Yeah. When we do subtraction of these two fractions, you can see a lot of cancellation. 1 cancel out. 5 cancel out. Then 2 root 5, negative root 5, but minus, right? Minus, negative, plus. So 4 root 5 over 4. 4 cancel. Root 5 left. Root 5 and this root 5 cancel out. You get 1. If you can work on it carefully, yeah, slowly, carefully, you will get this 1 value. So that means F2 also correct in our verification. Then the last one for this video, F3, yeah, this one much more challenging than before. Yeah. All right, but We like to do it because we can test our mathematical skills manipulating special algebra expressions. All right, so if we use the old way to do it, too much computation work, right? Yeah. Although if someone is really patient and work really carefully, slowly, yeah, they can do it. Yeah. But here, in this kind of situation, we try to avoid complicated calculation. We try to do it in a smart way to make the calculation relatively easier for us. All right, so let's work on it. First, we know we observe the reason. If we calculate it directly, it is hard. The reason is, observation. The degree of the phi too high. The higher the degree, the harder the calculation. That's our observation. But how to make it easier? The next question, how to make the calculation easier? We use a special strategy here. We need a strategy in this situation. So the strategy is targeting the relatively high degree of the golden ratio expression, reduce the degree to make the calculation easier. Is it possible we can reduce the degree? We have the same expression, but same value, but degree will be lower. If we can do that, then we can make the calculation easier. All right. Question. How to reduce the degree of phi cube? Phi cube. Yes. Using the properties of golden ratio. Golden ratio has special properties, right? Golden ratio. It is a very special number, so it should have some very special properties. So we use the properties. All right. So let's look at that. Okay? Yeah. First, phi cube, we can write it as phi times phi squared. How about that? Transform. Yeah. Here I use the transform idea another time. Transform the formula. Why? The reason simple. When we get stuck on some particular formula, usually to solve the problem, we need to do some appropriate transformations. Here, we just do that. So we use a different expression, phi times phi squared. Why we split? Why we split phi cube as phi times phi squared? The reason is we want to apply some special property of golden ratio. So what's that property? We know golden ratio phi is a root of this quadratic equation, right? So that's the equation, original equation. We derived the golden ratio number. So we go back to that point. So we can plug in the phi into this equation, so we get this expression. Phi squared minus phi minus 1 equals 0. So this is an identity. This identity, we can rewrite it in different ways, right? Also transformation. we also do transformation on this identity. So we have two different versions. The first version, phi squared equals phi plus 1. That's correct, right? So we just move the minus phi term, minus 1 term to the right-hand side of the equality. So we get this formula. First property. Second property, 1 equals phi squared minus phi. 1, see? Constant 1 can be represented as phi squared minus phi. Also, very useful. Yeah. So here we have these two properties. Yeah. So we save here. Then let's work on this. We will use directly. All right, so let's do the work. Let's continue our work. Replace phi squared by phi plus 1. How about that? Okay. When you do this substitution, can you bring down the degree of the whole expression? Yes. Yep. So this time, the highest degree is 2, lower than original degree 3. Right? Then we can bring down furthermore, because here you have a phi squared term. Can we use this property another time? Replace phi squared by phi plus 1 another time? Yes. After the substitution another time, we get 2 phi plus 1. Yeah. Same value as the original expression, but the degree of the phi term, highest phi term, just 1. That is low enough. Yeah, because we are very confident to handle phi with highest term degree 1. We don't have any problem. Work on it. Yeah. So let's put it here temporarily, and now let us work on 1 over phi cubed. Phi cubed this time is at the denominator, so it will be harder. Now, so usually we know when some expression, complicated expression is at a denominator, it will be harder to work on. All right, so let's work on this one, still using special properties of the golden ratio, but this time the trick is smarter than before. Yeah, we use smarter tricks in this step. All right, so first, this time, the numerator is 1. We substitute 1 by phi squared minus phi. Why we do that? Why? Because we know 1 is the simplest possible expression. Why you make the numerator more complicated, right? This time you make the numerator more complicated. Phi squared minus phi is more complicated than the original numerator. You will see we will get a benefit. When you do this way, there is a common factor between the numerator and the denominator. Common factor phi. So you can do cancellation. Otherwise, you cannot do cancellation, right? Yeah. That's the reason. After the cancellation, we get a phi minus 1 over phi squared. The degree of the denominator is lower, from phi cubed to phi squared. Is that good? That's good. Yeah. All right. So now let's replace this one by phi squared minus phi another time. How about that? Replace 1 by phi squared minus phi another time. The reason also simple, same as before. We want to have another common factor situation between the numerator and the denominator. Now, so after simplification, you can see the numerator becomes 2 phi minus phi squared. Then denominator phi squared, another cancellation phi. After that, 2 over phi minus 1. Denominator is just a phi. That's simple enough, right? Yeah. So you see, yeah. After we do some transformations, we get this new expression. At least the degree of the denominator much lower. Much lower. And degree is just a 1. And we have the confidence to handle that. Now let's combine these two terms. Phi cubed plus 1 over phi cubed. All right, adding these two numbers, right? 1, negative 1 cancel out, right? 2 common factor, we factor it out. Parenthesis phi plus 1 over phi, that is just, what's that? F1, right? So we get F3 equals 2F1. We know F1 equals 1. So F3 equals 2. See? In this way, we find the value of F3. But we use some tricks. We didn't do very complicated, so root 5, that kind of complicated computation. Although we can, if you like, you can try that way. Yeah, but I don't like use that way. Yeah. So here we use this special way. We take advantage of special properties of the golden ratio. All right. Now we successfully verify n equals 3. 0, 1, 2, 3. So that's enough. We don't need that many. We just practice a little bit. So next video, we will work on the general case, general n case, by mathematical induction. Yeah. All right, so let's stop here. Yeah.